Hello, and thank you for tuning into this talk. My name is Stefan Mann, and I'm responsible for technical marketing and technical sales at GAMS. Today, I'm going to talk about our new product, GAMS Engine, which is a system that allows you to easily run GAMS jobs on centralized compute resources or in the cloud. And in the next 20 minutes or so, I'll try and give you an idea of the underlying design of GAMS Engine and how you can use it in your own modeling projects. I will show a bit of Python code that illustrates the use of the API and the key concepts when connecting to Engine. Before I'll start, I would like to spend a minute on introducing GAMS for those of you who do not know us. GAMS stands for General Algebraic Modeling System, and as the first algebraic modeling language, it can trace its roots back to a World Bank project 3 decades ago, more than 3 decades ago. Since then, algebraic modeling languages have become mainstay tools in a lot of areas, and GAMS has been one of the main tool providers in this area. Currently, we have offices in the US and in Europe with around about 25 full-time staff. Our core competencies are obviously in the development of algebraic modeling software, integration of a range of different solvers with the software, and everything that goes along with this, such as platform-independent software development techniques, software quality assurance. Of course, we offer excellent support for the software and the bundled solver products. We offer consulting services, and we have always a range of projects with an extensive partner network. Our customer base is all around the world, both from academia and from commercial companies, with a large percentage of them coming from the areas of energy, economics, logistics, and operations research. Our core product, of course, is the actual GAMS distribution, which consists of the platform-independent modeling language and a whole range of commercial and academic solvers, which are included in the installation file. Part of this package are also APIs for C++, Java, Python, MATLAB, and other programming language. So you always have the opportunity to control GAMS from your own source code. We also include a development environment called GAMS Studio. You see a screenshot here, which allows you to edit your code and interact with it. So run it, analyze the results to some degree. So this is the way GAMS has been for a long time, but in recent years, it has become more and more obvious that the usage pattern of this kind of software, so of algebraic modeling systems, has shifted a bit. So where you used to have a modeling expert who was responsible for development and implementation of a model and also for running it and analyzing the results, things tend to be more collaborative now. We have some large customers with offices scattered around different countries who would like to share models and modeling results between the different teams and locations. And of course, this calls for some kind of server-based solution, and we have developed 2 new products for this. One is called GAMS Miro, which is a graphical user interface generator, which can take and transform an existing GAMS model into an interactive web application. And all you have to do to get to this stage is to add annotations to the model code that tell GAMS Miro which inputs and outputs should be displayed in the user interface. GAMS Miro contains a rich set of graphical output options. In the screenshot here, you see a map showing some results, but you can also have the usual things like bar charts, line charts. We have a very powerful pivot table tool in there to slice and dice your data. So there's a lot you can do with Miro. Miro is open source, and you can always extend it with your own custom code in R. The other product we developed, and that's the topic of today's talk, is called GAMS Engine. That's a deployment solution that allows you to solve GAMS models on centralized or cloud resources. GAMS Engine provides a REST API for user and job management, has a powerful built-in job scheduling system as well. So let's look at a bird's eye view of Engine. It has a few main components. The most important one here is the so-called broker that provides a REST API to access Engine and is the kind of gateway between the outside systems and the Engine internals. And of course, our own tools integrate nicely with this API. So you can schedule jobs to run on Engine from GAMS Studio, from our development environment. You can schedule jobs from GAMS Miro, both in desktop and server version. Engine also contains a built-in web user interface, which is mostly useful for adding users and checking the status of jobs. And you can connect to it from custom clients, and I'm going to show that in a little while. So once you put a job onto the REST API, it is placed into a queue, or onto a queue, and from there it moves onto available GAMS workers. They will then solve your model and place the results back into a database, and from there it can be downloaded again via the REST API. So Engine comes in two different flavors. One is called Engine 1, which is essentially an add-on for our machine-based GAMS licenses. So that is a system that runs on your own hardware on a single server. And the other one, which is brand new, which was only released in late January 2022, is called Engine SaaS. And that's a cloud service operated by us, currently runs on the AWS data center. Both flavors of Engine offer the same REST API, so switching from one to the other can be as simple as just changing the URL in your source code to connect to a different endpoint. Both contain a powerful GAMS job scheduling system, and both offer flexible worker resources. There's a difference here, though, between Engine 1 and Engine SaaS, in that with Engine 1, all the workers run on the same underlying hardware, so they have to share the hardware resources. While with Engine SaaS, each worker spins up in its own Amazon EC2 instance, so you have a lot more computational power available. And since we use Kubernetes to control this AWS cluster, we get auto-scaling, which means we have the ability to spin up as many EC2 instances as are required for the job at hand. So Engine is realized as a stack of Docker containers, which communicate through an internal Docker network. So if we start on the left here, you see the broker container that provides the REST API and also all the bits that are required for the graphical user interface. There's an Nginx server in here that provides the user interface. So once a job is placed via the REST API, it is put onto the message queue, which is realized as a RabbitMQ service running in its own container. And from there, the jobs are put or scheduled to run on the available workers. Each worker itself contains a full GAMS installation and Python as well. And the workers will pull the required data for the jobs from a MongoDB database. So data goes from the MongoDB database into the workers so they can solve the job. And then the results will be placed in a PostgreSQL database. And from there, they can be downloaded via the REST API again. So now I would like to dive in and show you how you can develop your own custom client in Python. I hope some of you are familiar with Python and can follow along. So first we need to take care of authentication. For this, we need to use the requests library, which is a very nice Python library that allows you to interact with REST APIs in a very, very easy way. So we import requests and the authentication class from the auth submodule of the requests library. And then we just take our username, in this case it's John Doe, and a password, which I've stored in a variable, to create a AU object, which is then later on used to authenticate our user. And we save the URL of our Engine SaaS in this variable URL. Then we can make the first request to the Engine API. And first, we would like to know what kind of instances our user John Doe can access. So we make a GET request to the usage instances and then the username endpoint of the API. And the results are then returned as JSON in JSON format. And I'm not going to go through all the details here, but highlight just a few parts. We get a field called instances available. And in there we see we have one instance here that's called times Z1D large, which has 1.8 CPUs and almost 16 gigabytes of memory. And we have another instance type, which is called GAMS Z1D X large A in this case, which has 3.8 CPUs and almost 32 gigabytes of memory. So you might ask, why do we have these strange values? Why do we have 1.8 CPUs? The reason for that is that Kubernetes itself needs to reserve some of the compute resources for itself. So the AWS instance offers 2 CPUs or vCPUs, but we can only pass on 1.8 of those to the user. And the same is true for the memory. So now that we know what kind of resources we have available for our job, we can prepare and submit our first simple example. So the model here that I'm going to use is called transport. That's from our model library, which is a simple linear programming example for finding the most cost-efficient way of shipping some goods from a number of factories to a number of markets, given the distance between the factories and the markets and the cost per distance for each crate of produced goods. So we have to create a zip file containing all the files required to solve the model. In this case, that's only the one file, transport GMS. Then we have to prepare a Python dictionary, which contains some information about the model we want to solve. So that's the name of the model, the namespace we would like to use on GAMS engine. So different users on engine are separated into namespaces, so you cannot see model data from other users. And we have to tell engine the label that describes the instance we would like to use. Then we need to create another dictionary containing the zipped model data, and then make a post request to the jobs endpoint of the API, passing in the parameters we defined before. And in response, we will receive a token, which uniquely describes this job on GAMS engine. So we can go back the next day or next week and download the job results whenever we need them. So two things I would like to, or one thing rather, I would like to highlight here, and that is just by changing this simple string here, we can choose the hardware to run. So if we have a small model and we know 16 gigabytes is enough, we can just use this instance type. But if we have a larger model, we can just change this value here to a different instance, and automatically engine will spin up a larger instance, and we can go up to 4 terabytes. So anything between 16 gigabytes and 4 terabytes we have on offer. So once we've submitted the job and we have our token, we can then request to get some information about the status of this job. And we just make a GET request to the jobs followed by the token endpoint of the API. Again, the response will be delivered as in JSON format. And when we look at some information here, we see a status value of 10, which in GAMS engine terminology means that the job is finished successfully. And we have results exist true, which means we can download the results. Okay, how do we do that? We make another GET request to the jobs plus token plus result endpoint of the API, and we will then receive a response that contains zipped data. So we just write this zip data to file, and if we look at the contents of the zip file, we'll see that it contains the GAMS log for the run, a copy of the model file, and the list file. And here's a section of the log that shows that we indeed have solved the model using Cplex, which found an optimal solution in 4 iterations. So that's exactly the same output you would see if you were to run GAMS locally on your own machine. So now let's go one step further. Suppose you have a GAMS model that takes a long time to solve and you would like to perform a parameter sweep on that model. In the case of our very simple transport models, we might want to know what happens to our objective value when we change the freight cost parameter. Very simple, trivial example here. And for this, we can define a so-called Hypercube job by creating a JSON file that contains several individual job definitions, where we supply a job ID So first scenario, second scenario, third scenario. And in each job, we change the arguments. So here our freight cost parameter is supposed to be 90 and 100 and 120. So these different values for freight cost are communicated to GAMS in the form of a compile time variable. So this is a line of our GAMS model where we set a scalar f to the value of our freight cost compile time variable. So these compile time variables in GAMS are always enclosed by percentage signs. So in each sub job of our Hypercube job, this freight cost parameter will take the value either 90 or 100 or 120. So to submit this Hypercube job, we have to zip everything up as before. We have to again create a dictionary with our model name, our namespace and the selected instance. And we have to create a second dictionary again with our model zip file. And in addition, we also have to submit or put our Hypercube description into this dictionary. Then we make a post request to the Hypercube endpoint of the API. And like before, we receive a job token that identifies the job. Now, what is really cool here is the fact that because we use Kubernetes, we get auto scaling. So in this case, we have 3 jobs, which then automatically spin up as many workers in GAMS engine SaaS as required to run those jobs. So we only need 3, but we could easily spin up 20 instances with 2 terabytes each if that's required. So if we had like a large energy systems model, for example, which uses a lot of memory, then we can get many more resources than we would be able to have locally in most cases. So after submitting the job, we can check on the status of our job like before, but by sending a GET request to the Hypercube endpoint and include the job token in our request here. And again, we get this JSON formatted output, and we see that the status is 10, so everything is done. We had 3 finished jobs. All of these 3 were successful, and we have the results available for download. When we download the results in the form of zip file again, and look at the directory structure of this zip file, we see that we have 3 subfolders contained in the zip file. And in each subfolder, we have a file called objective.txt, which was created by our GAMS model that contains just the objective value. We have a CSV file containing the different shipment arrangements that were produced by the model. We have a copy of our original model data, model file, and the list file. And of course, in this case, because it's trivially small, that's no problem. But if you had a larger model where you don't want to have these redundant files contained in your output, you can easily tell Engine to exclude certain files from the output to save on bandwidth. And each of these folders that was created in the zip file corresponds to the ID of the Hypercube jobs. So first scenario, and so on. Yeah, and from there on, you can just use any of the tools you have at hand to extract and aggregate the data and analyze it in any way you would like. So what's the point of all of this, you might ask, and what can people do now with GAMS Engine that they could not do before? Well, I think there are 3 main aspects where Engine really shines and that makes a difference to GAMS users, apart from the nice API and the job scheduler. And I'm going to list 3 different areas here. So the first one is you have a spiky or burst-like compute pattern. For example, one of our customers, the US States Military Academy in West Point, they have around 4,500 cadets, and each of those cadets individually compiles their 8-term academic program. So they're all different, and that leads to some interesting issues with respect to course assignment, exam scheduling, and room scheduling. And we, that is GAMS, have produced a custom-made solution for West Point to come up with good solutions to these issues. And that requires a fair amount of compute power, but only really every few weeks or months. So Engine SaaS is a great solution here because it quickly scales up when needed. And if it's not needed, then it doesn't produce any cost. The next aspect is when you have fluctuating resource requirements in terms of the amount of CPU or memory that you need. And we have two customers here that I would like to mention. One is the International Energy Agency's Energy Technology Systems Analysis Program, or ETSAP. They have developed an energy model called TIMES, which is available to all member states. So this ETSAP program currently has 21 member states, and each state can access this TIMES model to solve scenarios, energy scenarios, either on the national, the multinational, or even the global level. And depending on the scaling of this, you can get away with running this on your laptop or PC. But if you want to run a global model, you obviously need a lot more memory, and that's where Engine can provide those resources when required. And the second customer in a very similar position is the World Bank, specifically the Power Systems Planning Group of the World Bank, which also has a data-based electricity planning model, which can run on regional, country, or continental scale. And again, the small versions of this model can run on local computers easily. But if you go big and run it on a continental scale, then you might need a few terabytes of memory, and Engine can supply that easily. And the last aspect I would like to mention is model sharing and making models available to a wider audience. We have, for example, several projects with the UN's Economic and Social Commission for Western Asia, or ESCWA. ESCWA develops economic CGE models for clients. So the clients are states. And it can make them accessible to policymakers in those countries. So they can run different scenarios of these CGE models. And on top of Engine, UNESCO also uses GAMS Miro. So these models can be provided to policymakers to just run in their web browser with a nice graphical user interface. So that the users don't have to install any software locally, they can just run it from their web browser. I would like to mention before I finish two more ways to connect to Engine. Obviously, our GAMS Studio allows you to run models on Engine by just selecting Run GAMS Engine. Instead of Run would run it locally. Run GAMS Engine would connect to Engine, submit the job, and download the results automatically. And of course, it integrates with our fantastic UI generator, GAMS Miro. Here's the URL if you want to read more about it. And with that, I thank you for your attention. If you would like to have any more information, please don't hesitate to contact us. And thank you very much. Goodbye.